In this video, we're going to look at converting between rectangular and polar forms for coordinates. And in a previous video, I went through and I related the polar point to the rectangular point, and we came up with the following conversion formulas where we have x equals r times cosine of theta, y is equal to r times sine of theta, and x squared plus y squared is equal to r squared. Now the one part that we did not do in the previous video was talking about how to find theta in terms of the angle of rotation for the polar form. And the process is going to be very similar to how we went through this in previous units, like for unit circles, for vectors and parametric functions, where we want to find the reference angle. And by doing that, in terms of y and x, we're going to use the tangent function, because tangent of an angle on the coordinate system is equal to y over x. So that means our reference angle is going to equal the inverse tangent of the absolute value of y over x. So that way I do not have to worry about the signs of y and x, and this is going to place that reference angle back in quadrant 1 where I have both positive x's and positive y's. The reason why we have to do this is because of the restrictions there are for our inverse trig function. There is no single inverse trig function that has a range of from 0 to 360 degrees or 0 to 2 pi radians. So for that reason, we're just gonna use tangent, and we're gonna move our angles around as needed. Where if I am given a point that lies in quadrant 1, whatever I get for theta when I do inverse tangent is gonna be my answer, because all reference angles lie in quadrant 1. If I lie in quadrant 2 for my point, if I'm in degrees, the quadrant 2 angle will be 180 degrees minus theta, or if I'm in radians, it'll be pi minus our reference angle of theta. Quadrant 3 would be in degrees 180 plus theta, or in radians it'll be pi plus theta. And then finally in quadrant 4, I would do 360 minus my reference angle, or if I'm in radians, 2 pi minus theta. And so we're going to do a couple of examples for each one here. And so let's look here at this first one. We want to convert from rectangular into a polar point, and I got to pay attention here, and it says do it in degrees. So in doing so, our conversion formulas say, all right, we're given a rectangular point, so I have x by y. And x squared plus y squared is equal to r squared. So I would solve for r first. So 3 squared plus 4 squared is equal to r squared. And that's a Pythagorean triple. R is equal to 5. So I have one piece of that polar point. Well, now I need to find theta. Now, this lies in quadrant 1. And I just keep that in mind, so that way I know if I need to do any adjustments. Well, tangent of theta is equal to y over x. And we're going to do inverse tangent of the absolute value of y over x, which both x and y are positive, so it doesn't really matter if I have the absolute value there or not. And in degrees, we get theta here to be, it's going to come out to be 53.13 degrees. Now, because we're in quadrant 1, our angle is equal to the reference angle. So our polar point here is going to be r by our angle of revolution. So it would be 5 by 53.13 degrees. Now let's look at a second one. So again, here we're given a rectangular coordinate, so x by y, and I want to find the polar form of that point. And I'd start by finding r, the radius part of the polar point, and x squared plus y squared is equal to r squared. So we'd have negative 7 squared plus 24 squared is equal to r squared. And we solve for r in doing that, and we would get r to be 25. So I have one piece here. Now we need to find the angle part for our polar point, And so to find the angle, tangent of theta is equal to y over x. And to find our reference angle, so our reference angle for theta is going to equal the inverse tangent of the absolute value of y over x, so 24 over negative 7. And so what we have when we're doing that, we got to just make sure we're in the correct mode here, and we're in degrees. We get theta for our reference angle to come out to be 73.74 degrees. Now, that's not my final answer. That's my reference angle. Now, this point we're given lies in quadrant 2. So in quadrant 2, our angle is going to be 180 degrees minus the theta that we just got of 73.74. So 180 degrees minus 73.74, and that's going to give us the angle of rotation measure of 106.26 degrees. So this is the reference angle. So my not the reference angle, the angle of revolution. So my polar point is going to be 25 by 106.26 degrees. Okay, now let's do the same thing where we want to convert our given rectangular point into a polar point, but now this time we're going to be in radians. All right, so the process itself doesn't really change in terms of me solving for the angle. If I'm using my calculator would just have to be in radian mode, and my adjustments based off my reference angles are going to be either adding or subtracting from pi or taking away from 2 pi if it doesn't lie in quadrant 1. And so, first example here, we're given the rectangular point negative 11 by negative 60. So it's rectangular, so I have x and y. We'll go find r first. So x squared plus y squared is equal to r squared. So negative 11 squared plus negative 60 squared is equal to r squared. And we solve for that, and it's going to give us r to be equal to 61. So we got one big piece of the puzzle here for the polar point. The next thing we're going to do to help us find our angle is we're going to use a tangent function. Tangent of theta is equal to y over x. And we're going to find that reference angle. So our reference angle is going to equal the inverse tangent, and we're going to do the absolute value of y over x. So the absolute value of negative 60 over negative 11, which is technically positive. And we're in radians. So our reference angle in radians is going to come out to be approximately 1.39 radians. Now, this coordinate we're given, it lies in quadrant 3. So that negative 11, negative 60 is a quadrant 3 angle. So our angle measure, in this case, is going to equal, quadrant 3 says do pi plus our reference angle. So our angle is going to come out to be pi plus 1.39 radians, which is going to give us approximately 4.53. So the polar coordinate here in radians is going to be 61 by 4.53 radians. And one more example here. All right, so now we're given the point 13 by negative 84. It's a rectangular point, so x is 13, y is negative 84. We'll go solve for r. So x squared plus y squared is equal to r squared. So 13 squared plus negative 84 squared is equal to r squared. And we do that to solve for r, and we get r to be 85. Now I just got to find the angle measure. And so we'd use the tangent function. Tangent of theta around on this coordinate plane is equal to y over x. And we're going to solve for that reference angle. So the reference angle of rotation is going to equal the inverse tangent of y over x in this case. So negative 84 over 13. And we're in radians, so we're going to get theta for our reference angle. It's going to come out to be approximately 1.42. And now, since this coordinate lies in quadrant 4, our angle measure, so our angle that's going inside of our polar point, is going to equal 2 pi minus the reference angle that we just got. So 2 pi minus 1.42, and that's going to give us an angle measure that is approximately 4.87. And so we have the R for the polar point. So our polar point would be 85, and the angle of revolution in terms of this is in radians. So 4.87 radians. All right, now let's look at going the other way. So in this part, we're given a polar point, a polar coordinate, and we want to convert it into rectangular. We're going to do 2 examples of this. These are actually much easier. So we're given the polar coordinate r by theta. So r is 3, theta is pi over 6. Well, our conversion formula says that the rectangular coordinate, or the component of x, is equal to r times cosine of theta. So x, in this case, is going to equal 3 times cosine of pi over 6. Well, cosine of pi over 6 is equal to the square root of 3 over 2, so 3 roots of 3 divided by 2. There's my x component. And then to get y is equal to r times sine of theta. So it'll be y equals 3 times sine of pi over 6. Well, sine of pi over 6 is 1/2. And so the y part of this coordinate is just going to be 3 over 2. And so our rectangular point, which is x by y, is going to be 3 roots of 3 over 2 by 3/2. Or if I had that typed into my calculator to get my answers, it would come out to be approximately 2.598 by 1.5. And let's do one more. This time we're in degrees. Now, the sign of r or theta is irrelevant in this process because the trig functions in the conversion formula will account for the correct signs that I need when I go from polar to rectangular. So here I want to get the rectangular form. I'm given r and theta, so x is going to equal r times cosine of theta. So x is equal to 4 times cosine of negative 240 degrees. And I do that, see, negative 240 degrees, cosine is going to have a value of negative 1/2. So that's going to make x to be negative 2. And then we're going to take the same approach and we'll do for our solve for y. So y is going to equal r times sine of theta. And so y is going to equal 4 times sine of negative 240 degrees. And y is going to come out. Now sine of negative 240 degrees is going to be the square root of 3 over 2. Where the square root of 3 over 2 times 4 is going to make 2 times the square root of 3. And so our rectangular point is x by y, so it'd be negative 2 by 2 roots of 3. Or if I use my calculator to get the decimal values, it'd come out to be negative 2 by approximately 3.46.